All right.
All right.
Okay.
Yes, go ahead, Anna.
Yep. So I think it's noon now. All right. So welcome everybody. It's very, very excited to have Brandon to tell us more about his results with Andy on the Superspace covariant and delta operator module. So all yours, Brandon.
Well, thank you so much, Anna. It really is great to be back. So last time it was sort of a co-invariant ring extravaganza, right? We started with the classical co-invariant ring, Rn. So we had one set of n commuting variables, capital Xn. We had this action of the symmetric group Sn on this ring, and we looked at this corresponding quotient, which is a graded Sn module. And there are these very nice classical results, one due to Chevalier, that says that this is, as an ungraded module at least, the regular representation of Sn. Emil Artin computed that the Hilbert series of this quotient is the Q analog of n factorial, and in fact, Artin even gave a basis of this quotient ring. And Lustig and Stanley gave a combinatorial formula for the graded Frobenius image of this thing involving the major index statistic on standard Young tableau. Okay, so this is kind of a classical story. And then we moved into this Garcia-Heyman picture that was introduced in the 1990s, where now you have two sets of n commuting variables, xn and yn, right? And you have a diagonal action of Sn on this quotient ring. So Heyman proved that as an ungraded Sn module, up to at least a sign twist, this is the action of Sn on size n parking functions. As for the Hilbert series, sort of building on Heyman's work and the shuffle conjecture of Haglund, Heyman, Remmelwer, Ulyanov, Carlston and Mellett proved that the Hilbert series of this, it's a bigraded Hilbert series now, is the generating function of the statistics area and dm on size n parking functions. And I should also mention that Carlson and Blomkov have an independent proof of this result that actually avoids the work of Heyman entirely. And as a bigraded Sn module, Heyman proved that the bigraded Frobenius image of this thing is Nabla En. Okay. And now we kind of moved into this new picture where you still have two sets of n variables, but the catch now is that one set of variables, the x's, is a commuting set of variables, whereas the other set of variables, the thetas, is an anti-commuting set of variables. So this ring that I call omega n is called the superspace ring. It shows up in supersymmetry in physics. And again, it carries a diagonal action of Sn. You can think about modding out by the Sn invariance. And now the difference is that basically everything is no longer a theorem, everything is a conjecture. And this object was studied by the combinatorics group at the Fields Institute in Toronto. So I kind of call these conjectures collectively the Fields conjectures, or the Fields conjecture. So as an ungraded Sn module, we're supposed to be getting the action on ordered set partitions of n, at least up to a sign twist. The bigraded Hilbert series should look something like this. We have two variables now. We have a z variable, which is our anti-commuting tracker, and a q variable, which is our commuting tracker. And we basically get this z to the n minus k times some q analog of an enumerator for k block ordered set partitions of n. And well, now we have a bigraded Frobenius image too. And this is supposed to be something that involves these delta operators, right? So again, this is all a conjecture. There's been some progress on this conjecture. Swanson and Wallach have proven that the sign isotypic component of this thing has the correct bigraded Hilbert series. And Sagan and Swanson actually have a conjectural Artin-style basis for this quotient ring. So that's what I went through last time. Are there any questions about this?
Yeah.
Okay, oh yes, Teddy.
Yeah, Brandon. And I think I like this earlier statement on the Hilbert series involving Q and T. And at the bottom, where you mentioned the fields conjecture, I know you evaluated at t equal to 0, but would that equality hold if t is not 0?
Well, let's see. So for t not to be 0, we would need another set of commuting variables here, right? Because a Hilbert series is an algebraic object. So that's kind of more along the lines of a conjecture of Mike Zabrocki that I'll be talking about later on.
Oh, okay, okay.
Anything else? Okay, great. So I'm really happy to give a talk in a seminar like this because I can give a whole talk and actually not mention any work that I did. I guess it's a good thing this wasn't a job talk, but now I can really kind of get into what I did with Andy. And in a sense, as I alluded to last time, what we basically looked at was an alternative model for this superspace quotient ring where these things that were conjectures previously will actually become theorems. And then we're going to have a bridge conjecture, which hopefully will let us ultimately prove the field's conjectures using our model, right? Okay. So in order to give our model a little bit of motivation, I'm going to talk about harmonic models, harmonic spaces corresponding to quotient rings. And to do that, I'm going to have to talk about a differentiation action of polynomials on themselves. So fact, we have an action, which I will denote O dot, of the polynomial ring, C brackets Xn, on itself. And how does this action work? Well, if I take one polynomial, f, and I want to act on another polynomial g, what that is by definition is you take f, you turn it into a differential operator, and I'll explain what that means in a little bit, and then you apply that differential operator to g. So what am I doing here really? Well, f can of course be written out in terms of the n variables, x1 up through xn. And then partial f is the differential operator that you get by replacing each xi in f with the partial derivative with respect to xi. And because mixed partials commute, this is a well-defined differential operator, and I can apply it to g, and what I get is another polynomial. So this is a differentiation action of the polynomial ring on itself. And this leads to, this induces an inner product on my polynomial ring. And what does this inner product look like? Well, if I have one polynomial f and another polynomial g, I'm going to define the pairing of f and g to be the constant term of f O dot g. So the rule here is you take f, you turn it into a differential operator, and you apply it to g. And I guess to really be kosher, I should say that this is a non-degenerate bilinear form. And in fact, positive definite. Right, so bilinearity is reasonably clear. And if you're wondering why this thing is positive definite, well, you can check that the basis of monomials will actually form an orthogonal basis, and any monomial paired with itself, right, is going to give you a positive number. Okay, so we have this differentiation action. And this leads to the following definition. So I'm going to let I, living inside C brackets xn, be any homogeneous ideal the associated harmonic space I perp living inside C brackets xn is, well, one way of saying this is it is the orthogonal complement to I under this inner product, as this notation would suggest. But you can also think about it as, well, it's the collection of all G in C brackets xn with the property that f o dot g is 0 for all f living inside the ideal I, right? Okay, so for any ideal that's homogeneous, we have an associated harmonic space. And if I go back to the previous slide, I mean, whenever you're studying a co-invariant ring, you have a homogeneous or perhaps multi-homogeneous ideal sitting around. And the basic idea is that you want to study the quotient of C brackets xn by I using this harmonic space instead. And, you know, how does this work?
Brandon?
Yes.
Clarification. You kept calling this inner product. So is F inner product G the same as G inner product or conjugate?
Yeah, so I'm sorry. I do tend to work over Q more often than C. So I should say positive definite bilinear form.
Okay. And the other one is you introduced the harmonic space. Is there a harmonic idea in the usual sense of some vanishing of Laplacian?
Well, yeah, certainly. So if I were to take F to be like x1 squared plus x2 squared plus x3 squared and so on, we would normally call the operator given by the sum of the partial derivative squared the Laplacian, if you're in a physics class. And a harmonic polynomial would be, you know, some polynomial that vanishes, right, when you apply that operator to it. So this is you know, sort of definition by extending that analogy a little bit. Does that make sense?
Yeah, annihilating space would be.
What was that?
Annihilating space would be a good term instead of harmonic. Annihilating.
Annihilating, yeah. So you could also say annihilating, but yeah, we tend to call these things harmonic spaces.
Okay, thank you. Sorry about that.
No problem.
Brendan, I also had a question. So another possible way to define IPERP, well, why say that it's F circle G equal to 0 rather than F bilinear form G is equal to 0?
Correct, yeah. So it is something you can check that this does agree with the perp in the sort of usual
I
sense.
see. So they are the same definition.
They are the same, and that's kind of a one-line proof.
Gotcha.
Yeah. Okay. Anything else? Bruce, your shirt is very Orwellian. Oh, you're muted.
It says at the bottom, which you probably can't read, that this is true for very large values of 2.
O'Brien never told Winston that in the book, but okay. Well, at any rate, so just as in linear algebra, right? Assuming I have a homogeneous ideal, I can write my polynomial ring as a direct sum of I and I perp. And this means that I have an isomorphism, at least of graded vector spaces. And if my ideal is closed under the action of a linear group, I also have an isomorphism of graded modules over that group between the quotient ring C brackets Xn modulo I and I perp. So we have these kind of two different ways of looking at a quotient ring, the quotient ring itself and the harmonic space. And, you know, in general, kind of what are some kind of pros and cons of these models? Well, of course, this thing has a ring structure. Which is good. Whereas this thing, I perp, is only a graded vector space. So we have a ring structure here. That's nice. Only a graded vector space. Maybe it's not as nice. We want as much structure as we can in our field. On the other hand, right, if I'm working inside a quotient ring, I need to work with cosets. F plus I. And, you know, as you have learned, if you have studied things like the Buchberger algorithm, working with cosets, it's non-trivial theoretically, it's non-trivial computationally. There are a lot of issues that come up when you're working inside a quotient ring. So maybe this is a little bit less nice. Cosets give you some freedom, but they also come with some issues. But here in IPERP, we have honest polynomials. It's coset free, right? And that's an advantage, right? When are two things equal? It's like when they're actually equal as polynomials, not when their difference lies in an ideal, which can be a difficult thing to ascertain, right? So this is why you might want to look at a harmonic space if you're studying a quotient ring. Okay, so that was some sort of general theory. Are there any questions about that? Okay, so how are harmonic spaces going to come up for us? What do these harmonic spaces actually look like? So fact. So let's take I living inside C brackets Xn to be, well, the classical co-invariant ideal. All right, so generated, say, by the n elementary symmetric polynomials. Well, then I perp is, well, let me just kind of write it out. It's going to be the set of all polynomials f in C brackets Xn with the property that ED as a differential operator applied to F is 0. For D equaling 1, 2, 3, up through N. So something just to check here, it suffices to show annihilation under generators of an ideal. So that's maybe not too surprising, but now the more interesting part of the fact is as follows. So this is equal to the smallest subspace of my polynomial ring containing the van der Waals determinant, which I'll write as delta n, and that's going to be an alternating idempotent times a staircase monomial. Right? So what's this thing? It's an element of the symmetric group algebra, and it's just a sum over permutations W and Sn of the sign of W times W. So one way of defining a van der Waals determinant is you take the staircase monomial and you alternate it, essentially. So it has to contain delta n, and it has to be closed under all possible partial derivatives. Okay, so if I want to think about the harmonic space to the coinvariant ring, right, the classical coinvariant ring, what I do is I take a van der Waals determinant, I close under linearity, I close under partial derivatives, and I'm done, right? And in fact, the harmonic spaces that we'll be looking at in this talk today, they're all going to be generated by van der Waals-like objects. So this business of take an alternating polynomial, then close under a whole bunch of differential operators, that's going to be kind of a recurring theme for how we construct these harmonic or harmonic-like spaces.
Brendan?
Yes.
So is this the analog of the fact that the Artin basis consists of sub-staircase monomials?
Yeah, so it's actually very similar to that fact. Right?
Yes, that's why I asked.
Yeah. So let's kind of talk about the proof. So thank you very much for that question, Bruce, because it kind of leads into this correctly. So you first show that, well, maybe I'll just call this thing temporarily Vn, if that's okay. First, you show that the vector space dimension of Vn is greater than or equal to n factorial. And this uses reasoning very similar to what Bruce was alluding to. You essentially look at the lexicographical leading terms of carefully chosen polynomials inside this space of polynomials Vn. So for example, if I took delta n itself, the lexicographical leading term would be a staircase. And you can show that by applying these differential operators strategically, you can get every possible sub-staircase monomial as a lexicographical leading term. There are n factorial of these, right? So let me just say, look at sub-staircase monomials, right? Okay, so that's kind of a combinatorial argument. And then, right, so what I basically showed there was it was a lower bound for the dimension. I showed the lower bound is correct. Now I have to show that the upper bound is correct. So then show that if I take any elementary symmetric polynomial, and if I apply it to my Vandermonde, what I get is 0 for D equaling 1 to upper n. So you might think that when I expand this thing out, it's going to be some huge mess of partial derivatives and polynomials, and I'm supposed to magically show that I get 0. But I want to convince you, no, that this is actually a really beautiful fact that you should be able to see in a pretty nice way. So how can I think about this thing, right? So I'm taking my ED, and I'll leave that alone for now. And I'm applying it to, well, officially, right, a Vandermonde determinant is epsilon n times a monomial. But I'm going to think about my monomial in a sort of graphical way. I'm going to think about it in terms of an actual staircase, right? So one way you can sort of write these monomials, one way I like to write these monomials is something like this. So this is, representing, I guess, the case of n equals 6, right? And I think of that staircase as being the monomial x1 to the 5th, x2 to the 4th, and so on. So I take that and I anti-symmetrize this sloppy notation, but I think I can get away with it in this form. Okay, now what am I going to do with this thing? This ED is a differential operator, but not just any differential operator. It's a symmetric differential operator. And that means I can move it past any permutation and actually any linear combination of permutations. So now I can say that this is epsilon n on ED, and I have this same staircase picture, 4, 5, 6, and I'm applying this thing as a partial derivative. So how can I interpret differentiation in a combinatorial way, right? So I can think about something like, I don't know, here's a formula that we try to teach our calculus students. The derivative of x cubed is 3x squared. But the way I'm going to look at this, right, is my x cubed is going to be a column of height 3. And taking an x derivative of an x cubed will correspond to putting a red dot in one of the possible squares of my column, right? And when I put the red dot in, you think about kind of removing that box. And I guess there are 3 ways to do this, and that's going to lead to this coefficient 3 up here. Okay, so moving up, what if we have a whole bunch of variables, right? How do I think about applying an ED to something like this? Well, I have to put red dots in different columns, right? So I put red dots in, well, maybe 3 different columns like so. So this would kind of correspond to the case of D equal 3. And I do this in all possible ways. That's how I model applying ED as a partial derivative operator to this staircase monomial, right? You can just sort of work this out. But now what's going to happen when I apply my alternate, right? Because I started with the staircase and because I put in at least 1 red dot, I have forced in any situation 2 of these columns to have the exact same height. So now this alternate's going to come in and it's going to kill every single monomial, right? So what I get is 0. Okay, so any questions about that? Kind of a combinatorial way to think about taking derivatives. Great. Bruce is happy. I'm happy. All right. So this was all somewhat classical, and how might we generalize this? So finally we get to the definition that I had with Andy. So definition, Rhodes-Wilson. So I am going to let K be less than or equal to N. So the superspace Vandermonde delta NK is going to be some kind of element of omega n. And it's given as follows. So delta NK is going to look like x1 to the k minus 1, x2 to the k minus 1, up through xn minus k to the k minus 1. So I have an initial segment like this. Now I have xn minus k plus 1 to the k minus 1, xn minus k plus 2 to the k minus 2, down to xn minus 1 to the first, xn to the 0, times theta 1, theta 2, up through theta n minus k. And to all of that, I apply my alternating idempotent, I apply epsilon n, right? Okay, so this is some kind of an element of superspace, and the idea is that, well, delta n comma n doesn't involve any theta variables at all, and is just this classical Vandermonde determinant, right? So we're defining these new superspace elements. And of course, I think when you see a definition like this the first time, it's almost impossible to read. So I think it's kind of good to have a picture that goes along with this thing. So maybe let's look at delta, oh, I don't know, 6, comma 4. So this is going to be epsilon 6 will apply to some kind of a monomial. So I guess we're going to have three copies of the exponent 3 here. And we're going to see 2, we're going to see 1, and we're going to see 0. But now the catch is that these first two variables, x1 and x2, are going to have these kind of friends. They're going to be multiplied by theta 1 and theta 2. And now when I apply epsilon 6 to this thing, well, if I didn't have the thetas, I would just get 0. But because I have the thetas, I get something non-zero, right? So the thetas are what allow me to get non-zero elements out of this definition. So questions about this? Example. And what are we doing with these superspace Vandermondes? So here's another definition of ours. So in much the same way, oh yeah, Teddy?
Yeah, this is non-zero.
Yes.
It's never 0. I think that's what you're saying, if I understand. That's enough, even if you have 1 theta.
Even if I have 1 theta, because what that would mean is that 2 of these columns would be of the same height, but 1 column would carry a theta and the other wouldn't. So kind of like here, we have 3 columns of the same height, 2 carry thetas, 1 doesn't.
Okay, got it. Thank you.
You're welcome. Okay, in much the same way that the classical harmonic space was in some sense constructed, was grown out of the single Vandermonde determinant, this module that I'm going to define, that I defined with Andy Wilson, is going to be built out of this delta NK, right? These superspace Vandermondes are in some sense seeds that can be used to grow modules. So I am going to let V in K living inside omega n be the smallest linear subspace such that, well, it's the same definition basically. Now, we're going to insist that this superspace Vandermonde be contained inside V and K, and we're going to insist that V and K is closed under all partial derivatives in the x's. And if you're wondering, how does a partial derivative in the x's act on superspace? Well, it just annihilates all thetas. It treats the thetas as constants, if you like. Okay, so it can be shown that this guy V and K is actually a graded SN module. And now we actually have a theorem which says that the graded Frobenius image, the graded character of V and K, gradient factor Q, is delta prime EK minus 1 on EN after sending T to 0. And I remind you that this particular symmetric function was exactly the thing that was appearing inside the Fields conjecture. So the Fields conjecture is a conjecture involving a superspace quotient where they think this is the graded character. And now we have a certain subspace of superspace where we know this is the graded character, right? So that's our theorem. And we have a bridge conjecture. So the bridge conjecture states that the linear map given by a composite, so first you take a direct sum over all K of V and K. This is naturally embedding inside superspace omega n, which in turn has a canonical projection onto the superspace coinvariance, is a bijection. And this bridge conjecture, if true, would imply the Fields conjecture. It would imply the Fields conjecture because inclusion and projection are about the nicest maps of graded SN modules you can hope for. All right, but frustratingly, even though this is a fairly elementary statement, you're just trying to prove that a certain linear map is a linear isomorphism, we have not been successful so far in doing this. All right, so how can we hope to outline a proof of this theorem? Copy. Paste. So proof outline. So step one is you show that the vector space dimension of V and K is bigger than or equal to K factorial times S in K. So you show that the vector space dimension has what turns out to be the appropriate lower bound. And I'll just say the way you do this is you look at monomials. Right, a somewhat combinatorially intricate argument, but in a sense, at a theoretical level, there isn't as much going on here, right? But how do we get the relevant lower bound, and how do we talk about the graded SN structure? Well, we have this other result. Mine joint with Jim and Mark Shimizono. that says that if we let R and K be our polynomial ring modulo an ideal I and K, with I and K being generated by the kth powers of the variables, and not all of the E's, but only the top K of them, then the graded Frobenius image of R and K on Q is, well, almost this thing, but it's got a little twist to it. It's got an omega, and it's got a grading reversal that I'll denote by rev Q, right? So we have a quotient of the polynomial ring, only commuting variables this time, that has, well, almost the right graded SN structure, but it's got a grading reversal and it's got a twist by omega. So we're going to exploit this result. So maybe this is a step 2 here, by showing that I and K annihilates delta in K under this action of partial differentiation. And let's think about this, right? Whereas multiplication increases degree, partial differentiation lowers degree, so that kind of accounts for this grading reversal here. And furthermore, when I was generating the module V and K, it's generated by a superspace Vandermonde, and whatever else a superspace Vandermonde is, right, it's certainly alternating, right? So that's going to give me a sign twist. And how are we going to do this? Right, how do I show this annihilation? Well, it's going to be an extension of the argument I talked about in the case of only commuting variables, right? So here's delta 6,4, right? I take this staircase that kind of plateaus and is augmented with these thetas. I apply an alternate to it. And I want to show that it's going to be annihilated by, well, all possible xi to the fourths, and also, I guess, the top 4 elementary symmetric polynomials. So I guess let's have a think about this. If I were to apply like delta or partial x1 to the 4th, or any partial derivative to the 4th power, well, my maximal column height is 3, so I certainly have annihilation there. But it gets a little bit more interesting when you consider what happens when you apply these elementary symmetric polynomials as partial derivative operators, right? So if I take delta 6,4, and if I try to apply E3 to it, say, as a partial derivative operator, and E3, by the way, is the kind of lowest degree elementary symmetric polynomial in this relevant quotient. Well, I can do the same argument, right? Where I can say I have a symmetric differential operator. It moves right past this element of the symmetric group algebra, this epsilon 6. Copy. Paste. And now I'm thinking of applying epsilon 3, or E3 rather, sorry, to this staircase monomial, where now my staircase monomial involves thetas. So again, we have these red dots. And the thing to observe is that because only 2 of my columns have a theta, right? And I have to put 3 red dots down in different columns, at least 1 red dot appears in a non-theta column. And this is a general phenomenon. If I'm looking at the generators of my ideal I and K, my lowest degree generator has precisely the degree necessary for at least one of these red dots to be forced outside of a theta column. And that's good, right? Because now I want to say that this alternate is going to kill every term in this expansion. But if all of my red dots were in theta columns, right, thanks to the thetas, the alternate would not actually kill, right? You might have 2 columns of the same height, but because the theta is anti-commute, right, I can't actually conclude that applying this epsilon 6, or in general applying the epsilon n, would kill my monomial. But because the degree of my elementary symmetric polynomial is sufficiently high, what I get is 0 there, right? So again, it's a combinatorial argument that shows annihilation. So I recognize that this was perhaps a little bit fast and also a little bit informal, but are there any questions about that?
I had one question.
Sure.
So let's say in this exact example, so the red dot in the 5th column means your coefficient of x5 and x6 are both, there's no power.
Yeah, the exponent is both 0, yeah.
So when you interchange x5 and x6, that term will give 0.
Correct.
Right, but what about if you're at the same time you're interchanging x1 because of the theta, they'll introduce like minus sign, won't it?
Oh yeah, you're right about that. But what you're really saying is that this guy inside the symmetric group algebra is going to factor as a 1 minus 5, 6 times G.
I see. So yeah, summing over all of them. I see it.
Yeah. Yeah. So once I sum over all of them, that actually takes care of it. Yeah.
Okay.
Good question. Anything else? Okay.
Yeah, question, Brandon.
Sure.
And in the Hagland et al. Statement, there is a twist that you put by the red.
Yes.
How do you get rid of that to get your result with Wilson?
That's the magic of partial differentiation, right? Because whereas multiplication makes you go up in degree, partial differentiation makes you go down in degree. So that's how this reversal is taken care of. And furthermore, what about this sign twist? Well, remember that V and K was generated by an alternate, so it looks something like this. So when I consider the quotient module coming from this action, really, it's going to automatically carry this sign twist. Is that okay?
Mm-hmm. Yes, thank you.
You're welcome. All right. So what else to say? Let me just kind of make a remark, sort of tying this back into the Fields conjecture. So the Fields group has a, again, conjectural description of the harmonic space to SRN, right? So if we look at the actual superspace coinvariant ring, this is a quotient of superspace. There is a theory of harmonic polynomials that holds within superspace, right? So we have these partial x derivatives still, and there is a way to differentiate, if you like, with respect to an anti-commuting variable. There are some signs involved. So you have an analogous theory of harmonics, and in this group at the Fields Institute, conjecturally at least, has a way to describe this actual harmonic space. And unlike the case of V and K, you don't have a single generator. You have 2 to the n-1 different generators. The generators, again, are kind of Vandermonde-like, and it might be interesting to kind of tie in their generators with ours, but we haven't been so successful at doing so far. So I guess in the 9 minutes I have remaining, I want to address the question that Teddy asked close to the beginning. What happens if you try to throw the T back in? Well, there's something called the Zabrocki conjecture. Due to Mike Zabrocki. And he considered a ring over the complex numbers where you have 2 sets of commuting variables, like in the Garcia-Heyman work. And you also have 1 set of anti-commuting variables, like in Superspace. So these variables are bosonic, they commute. And these variables are fermionic. So this carries a triply diagonal action of Sn. And we can think about what happens when we mod out by, well, the usual thing, right? The space of Sn invariants with vanishing constant terms. So now I have a certain quotient ring. And it's going to be a triply graded Sn module. And to talk about its tri-graded Frobenius characteristic, I need 3 grading trackers. I need a Q, which is keeping track of the X variables, a T, which is keeping track of the Y variables, and a Z, which is keeping track of the theta variables. And Zabrocki conjectured that if I look at this thing and if I sum, okay, well, I have a Z to the n minus K out front. And now I actually have this delta operator, delta prime ek minus 1 on En. So that's the Zabrocki conjecture. And as a matter of fact, this conjecture has an analog in the world of superspace Vandermondes. So this is a conjecture of Andy Wilson and myself. And so now I'm going to let bold-faced V and K be the smallest linear subspace of this big ring such that, well, first off, I want my superspace Vandermonde to live in this subspace. And to be very clear, when I say my superspace Vandermonde, I mean in the X variables and the theta variables. So I don't have any Y variables so far, although that will change in a bit. Secondly, I want to say that V and K is closed under all partial derivatives and commuting variables. And you might say, well, I don't have any y variables yet, so why include that? And that's going to change here. So I'm going to give you kind of one more thing you can do with your polynomials. You can apply polarization operators. So polarization operators look as follows. I have y1 partial x1 to the j, plus and so on up through yn partial xn to the j for j bigger than or equal to 1. So these operators are polarization operators. And what they essentially do is they take x variables and they turn them into y variables. Okay, so the conjecture with Andy is that if you look at this crazy space, bold V and K, it's not too hard to see that bold V and K is a bigraded, actually, SN module, right? It's concentrated in a given theta degree in minus K, but it carries a bigrading in the X variables and the Y variables. And the conjecture is that this thing is delta prime EK minus 1 on EN, right? So this is a direct analog of the Zebrocky conjecture, but now with van der Waals. So the Zebrocky conjecture, if you were to set the y variables to 0, you would get the Fields conjecture, and that's something that's still frustratingly open. But in this bold-faced V world, when you set the y variables to 0, you get this previous theorem that I had with Andy, right? So for some reason, that's a little bit of a mystery to me at some theoretical level. It seems easier to work with these superspace van der Waals than it does to work with superspace coinvariant rings. And I don't have a terrific explanation for this. I mean, in some sense, coinvariant theory is something very classical. It's something very nice. But apparently, it's not seemingly the easiest way to approach these kinds of quotient rings, or it's not the easiest way to get multigraded SN modules with these kinds of Frobenius images. All right. So I guess Marino will be going next. And my understanding is that he'll be talking about mathematics related to similar kinds of quotient rings, where you might say, well, why stop at 2 bosonic sets of variables, 1 set of fermionic? Why not have, say 2 sets of bosonic, 2 sets of fermionic? So there's a conjecture of Diodario, Arasi, and Van den Wijngaard that talks about the multigraded Frobenius image of that object. And that conjecture involves something called theta operators, not to be confused with theta variables. And that conjecture has seen some progress. So in the purely commuting case, it reduces to Haymann's result. And in the purely anti-commuting case, I was able to prove that recently with Marino and also with Sasha Arasi. And I guess with that, I am out of time. So thank you all for your attention.
Thank you, Brendan. So any questions?
Yeah, so I have a comment. Whoopsie. Yes, the dog made my comment for me. No. And a question. First of all, beautiful, beautiful stuff, Brendan, and beautifully presented. So I'm just struck by the parallels between these delta NK that you've constructed with Andy and what's in my paper with Josh. I mean, basically, what you're doing is you're taking delta K and allowing it to extend with columns of length K minus 1 and putting theta variables on, yeah, you can go back to, exactly, that's the picture. In our conjectured basis, you take it and you can put in columns of the same height anywhere you like in the staircase. And then of course, the new columns are all indexed by thetas. So it's, I don't know what to make of that. I just noticed it.
Oh, no. I mean, it's, there are a lot of things that seem to be parallels in this story, but, so somehow we can't make this quite precise. So to talk, for another example, if we want to look at this conjectural description of the harmonic space, what they're doing is they're taking this classical Vandermonde and the x variables alone and applying these operators, u1 to the epsilon 1 up through dn minus 1 to the epsilon n minus 1 to it, where dj is the sum on I of partial xi to the j theta j. So this is some kind of higher, or sorry, theta I. So this is some kind of like higher Euler derivation. And the Fields group conjectures that if you take these elements of superspace and close over all x derivatives, what you get is the harmonic space to this thing. And they can show that all of these superspace elements are harmonic by reasoning kind of very similar to what you're seeing here. And they can show that the vector space spanned by these things has the appropriate lower bound in dimension. But they can't prove that this exhausts the harmonic space, right? And I was Josh's postdoctoral advisor. I gave him the problem of looking at this thing and examining the graded SN structure. He's done terrific work on that, but even that problem was very hard. There are anomalies that show up when n equals 8. So things are getting pretty big there. It's sort of hard to say exactly what's going to go on.
Nasty.
But if you look at these polynomials, if you write them out, you see that the terms in this superspace Vandermonde live among the terms of the highest degree thing that you get in this way, right? So if I basically say that just an initial segment of my epsilon j's is going to be 1 and then everything else is 0, what I get is a superspace Vandermonde plus a whole bunch of other terms. So again, like it just looks so close.
Right.
So, yeah.
And my question was, how much of your work with Andy generalizes to the complex reflection group GMNP?
We have not looked at that. My suspicion would be that you would sort of scale all of your columns, right? And at least for the case of wreath products, right? Like GR1N, my suspicion would be if you scale all your columns by R, you're probably good.
Yeah.
Right.
That's exactly what happens in my paper with Josh in type B. You just scale the columns.
You double the columns.
You double the columns.
Exactly. Yeah. And I have not looked at that, so I should probably not be so bold as to make such statements. But
well, it sounds like your intuition is on the right track, at least.
Yeah. All right.
So I have a question. Can you go back to the last slide?
Sure.
So I'm just a little confused. What happened to the partial with respect to the theta i's?
Oh, right. So in this case, we actually don't need to take any partials in the theta variables, right? I defined other modules with Andy that I didn't talk about today, where you start with the superspace Vandermonde and you apply partials in the x's and partials in the thetas. And what you get there is a bigraded, right, SN module and x and theta. And this is something that actually exhibits a number of interesting symmetries. It satisfies some bigraded analog of Poincare duality. And we wrote kind of a follow-up paper which studies the combinatorics of these modules in terms of ordered set partition-like objects. So I guess I didn't quite get to those modules in my talks, but yeah.
All right.
Any other
Brandon?
questions?
Yeah.
Yeah, Teddy.
Yeah. Brandon, and you have now eventually this VNK as SN module, and like in many cases that you have been working with, what if you scale down the SN to a subgroup of SN?
What if I scale down the S into if I restrict?
Yeah.
Yeah, I mean, I guess I couldn't tell you anything besides the standard stuff, right? For any SN module, you can restrict to a subgroup, but I don't really know if you can get kind of surprising results through these particular modules in that way.
Yeah, because these are wonderful conjectures, but to make progress, if I want to see some special things.
Oh, well, I mean, so I mean, one issue is that, you know, let's say you restrict down all the way to the trivial subgroup. There you basically have, you know, multi-graded vector spaces, but we can't even show the dimension is right. So, I mean, you know, there is this kind of question of how do we incorporate SN structure, and we'd like to do that ultimately, of course, but we can't even get the vector space dimension right at this point. Like, you know, in this fields conjecture, you know, they can show a lower bound for this dimension, right? They can show it has the appropriate lower bound, but they can't get the right upper bound. And that's really frustrating, right? Because, you know, getting an upper bound for a quotient module should just involve a straightening algorithm, applying relations in a reasonably clever way, but nobody knows how to do this.
Thank you. Nice talk too.
You're welcome.
All right. So any other questions for Brendan? All right. So let's thank the speaker again because it's very nice stuff. Thank you, everybody. So we'll see you on Thursday. Bye.